You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Attention, in the context of artificial intelligence, refers to the remarkable mechanism that allows models to determine which parts of an input sequence are most relevant at any given moment. Unlike earlier methods that forced models to read inputs in strict, step-by-step order, attention provides a flexible framework for selectively focusing on important tokens, no matter where they appear in the sequence. To imagine this in everyday terms, think of reading a dense paragraph in a book. Your eyes may move linearly across the text, but your mind jumps back and forth, revisiting words or phrases that seem especially important. This act of highlighting and reevaluating is precisely what attention provides for AI systems. It ensures that, out of a sea of possible inputs, the most relevant pieces are elevated and emphasized, while less relevant ones fade into the background. This capacity to focus has been the central breakthrough that allowed transformers to replace older architectures as the backbone of modern AI. At the heart of attention is the query, key, and value framework, often abbreviated as QKV. Though it sounds mathematical, the intuition is straightforward. Imagine every token in a sequence carrying three labels. The query represents what that token is currently asking about. The key represents what it offers as a point of comparison, and the value represents the content it brings to the table. When a token's query is compared to the keys of other tokens, the system calculates how similar or relevant they are to one another. Based on this similarity, it retrieves the associated values and combines them into a context-rich representation. This triad, queries, keys, and values, provides the scaffolding for the model to decide what matters most in any given context. Even without the math, one can see how it mirrors human conversation. When you ask a question, query, you look for someone with the relevant expertise, key, and then you listen to their answer, value. The process of similarity scoring sits at the core of attention. Each query is compared against every key in the sequence, and the degree of match indicates relevance. High similarity means that a token strongly relates to another, while low similarity indicates weaker connection. Think of this as a form of spotlighting. When you ask a question about a topic, your mind naturally highlights the words or phrases that feel most closely connected, dimming out the unrelated ones. This scoring does not require exact matches. Instead, it identifies patterns of association, enabling the model to link concepts even when phrased differently. For example, in a sentence about financial markets, attention may highlight connections between investors, trading, and stocks, even though the words themselves are not identical. By computing these relevance scores, attention allows models to flexibly build contextual understanding that adapts to each input. Once similarity scores are established, the values come into play. Each value is weighted according to its relevance score, and then the system combines them to produce a new, context-aware representation for the token in question. This process is akin to blending advice from multiple experts, giving more weight to those whose input is most relevant to your current problem. The weighted combination ensures that the resulting representation captures the most important aspects of the entire sequence, not just the token itself. In practice, this means a model can understand that the word bank in one sentence refers to finance because of its high attention weight toward money, while in another it refers to geography because of its stronger connection to river. The weighting of values, guided by similarity scores, gives attention its ability to resolve ambiguity and adapt meaning based on context. A major refinement in this mechanism is the concept of multi-head attention. Instead of computing a single set of QKV relationships, models compute many of them in parallel, each head learning to emphasize different types of relationships. One head might focus on short-range dependencies, such as subject-verb agreement, while another might highlight long-range connections, such as themes across multiple sentences. Together, these heads provide a richer and more nuanced representation, much like listening to a panel of experts rather than just one. Multi-head attention prevents the system from being overly narrow in its focus and enables it to capture multiple layers of meaning simultaneously. Without this multiplicity, models would risk overlooking subtle or complex relationships that only emerge when inputs are viewed from multiple perspectives at once. Because attention operates without a natural sense of order, models require positional information to understand the sequence of inputs. In human language, word order carries meaning. The cat chased the dog is not the same as the dog chased the cat. To capture this, attention layers are supplemented with position encodings, mathematical signals that indicate where each token falls in the sequence. These encodings allow the model to distinguish between tokens, not just by their content, but also by their position, ensuring that relationships are understood in the proper order. Without position encoding, attention would treat the sequence as a bag of words, stripping away crucial structural information. This clever combination, flexible attention plus positional grounding, allows models to achieve both adaptability and coherence in processing text. Compared to older recurrent neural networks, attention introduces profound advantages. Recurrent models processed sequences one step at a time, carrying information forward in a chain. This made them slow to train, difficult to parallelize, and prone to losing information over long distances. Attention sidesteps these bottlenecks by allowing every token to consider every other token simultaneously. Instead of trudging through text word by word, attention leaps across the sequence in parallel, constructing a global picture of relationships. This change is why transformers were able to replace recurrent networks. They offer both speed and better long-distance understanding, combining efficiency with improved performance. The elimination of sequential bottlenecks was nothing short of transformative, reshaping the entire landscape of natural language processing. The scalability of attention, however, comes at a cost. Because every query compares itself to every key, the computation grows with the square of the sequence length. For short texts, this is manageable. But as sequences extend to thousands of tokens, the cost balloons dramatically. This quadratic scaling means that attention, while powerful, is not infinitely efficient. Engineers designing large-scale models must therefore contend with trade-offs, balancing the desire for longer context windows against the reality of computational expense. This tension has driven ongoing research into more efficient forms of attention that preserve power while lowering cost, a theme we will explore more deeply in later episodes. One of the best ways to understand attention is through analogy. Imagine reading a complex legal contract. Instead of paying equal attention to every word, you scan for relevant clauses, referencing definitions, and skipping boilerplate language. Your mental spotlight shifts dynamically, connecting related parts even if they are pages apart. Attention mechanisms in models work the same way. They shine focus on the parts of the sequence that matter most for the current interpretation, creating bridges between relevant ideas. This visualization captures the elegance of attention. It transforms flat, sequential text into a web of dynamic relationships, enabling deeper understanding than rigid reading would allow. Beyond flexibility, attention offers the massive benefit of parallelization. Because it does not rely on step-by-step recurrence, attention-based models can process entire sequences simultaneously. This property makes them far more efficient to train on modern hardware, which thrives on parallel workloads. Instead of waiting for each token to be processed before moving on to the next, attention allows GPUs and TPUs to crunch through sequences all at once. The result is a dramatic acceleration in training speed and scalability, enabling the creation of models orders of magnitude larger than what was possible with older methods. Parallelization is one of the key reasons transformers could become the foundation of scaling laws, and it remains one of their defining strengths. Attention also enhances generalization, the ability of models to apply what they have learned to new and unfamiliar contexts. By flexibly linking tokens across varied positions and contexts, attention builds representations that capture relationships beyond rigid memorization. This explains why attention-based models perform so well across a wide range of tasks, from translation to summarization to code generation. Their ability to generalize stems directly from the relational perspective that attention provides. Instead of memorizing patterns in one fixed order, models learn how different elements interact regardless of position. This adaptability makes them resilient, powerful, and broadly applicable across domains. Despite these strengths, attention mechanisms are not without limitations. The quadratic cost makes very long sequences unwieldy, and even with improvements, models can struggle to maintain coherence across book length or transcript length inputs. Additionally, attention by itself does not solve deeper issues such as bias, hallucination, or factuality. It provides a powerful structural tool but does not guarantee truth or fairness. These limitations remind us that attention is one component in a larger system, and that its effectiveness depends on careful integration with other methods for monitoring, alignment, and governance. Recognizing these limits keeps our view balanced, avoiding both overhype and underestimation. The role of attention in transformers cannot be overstated. It is the central innovation that redefined the field, enabling models to achieve breakthroughs in performance, scalability, and versatility. Without attention, the transformer architecture, and by extension the large-scale models we rely on today, would not exist. Attention is the mechanism that transformed transformers from a clever idea into a dominant paradigm, unlocking the potential of parallelism, long-range understanding, and scaling laws. It is no exaggeration to say that attention is the beating heart of modern AI, pumping relevance and context through the veins of every transformer system. Attention's power extends beyond text. In multimodal models, the same principles align tokens from different domains, words with images, sounds with captions, and even video frames with descriptive text. This ability to map across modalities demonstrates that attention is not tied to language alone, but is a universal mechanism for linking patterns across data types. Whether it is identifying which part of an image corresponds to a caption or aligning audio with transcript text, attention serves as the glue that holds multimodal understanding together. This extension beyond text underscores its fundamental nature, suggesting that attention is not just a linguistic tool, but a general principle of machine reasoning. Ultimately, attention serves as the foundation for scaling successes. Its flexibility, efficiency, and parallelism made it possible to train models that are larger, more capable, and more general than anything seen before. It is the mechanism that underpins scaling laws, enabling predictable improvements as parameters and data expand. Attention is not only a technical innovation but a conceptual shift. It reframes machine learning as the construction of relationships rather than the memorization of sequences. In this way, attention stands as both the practical engine and the philosophical breakthrough behind the age of transformers. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Self-attention is the specific mechanism within transformers, where every token in a sequence considers its relationship to every other token in that same sequence. This is different from older models that only looked at a limited number of surrounding tokens. In self-attention, the word bank in a sentence can directly examine its neighbors like money or river to clarify meaning, no matter how far apart those words are. The magic here is that the model doesn't need to wait for context to arrive sequentially. It can access it instantly through the attention mechanism. Each token becomes aware of the broader sentence rather than being confined to its immediate surroundings. This broad view makes it possible for models to capture long-range dependencies, such as linking the subject at the beginning of a sentence to a verb much later. By giving each token access to the entire sequence, self-attention creates global awareness within a model, allowing it to understand language in a way that feels more fluid and human-like than rigid step-by-step methods. Cross-attention extends this idea by allowing tokens in one sequence to attend to tokens in another sequence, which is crucial for tasks involving multiple modalities or input sources. For instance, in machine translation, the English sentence on the input side is processed in relation to the tokens of the French sentence being generated. Similarly, in multimodal models, an image is broken into patches, each of which becomes a token, and the text tokens of a caption attend to those image patches. This creates an alignment between language and vision, letting the system learn which words describe which parts of the picture. Cross-attention is the bridge between modalities, enabling models to integrate different kinds of information into a unified representation. Without cross-attention, systems would struggle to combine text and images or other paired data. It is this mechanism that has made multimodal AI possible, allowing transformers to expand far beyond their roots in natural language processing. Masked attention is another variation designed for generative tasks, where models must produce text in a left-to-right order without peeking at future words. Imagine playing a guessing game, where you must fill in the next word of a sentence without being allowed to see what comes after. Masked attention ensures fairness in this process by hiding future tokens from the model during training, so it only considers past and present context. This causal structure is what makes autoregressive models like GPT effective at text generation. They learn to predict the next word based only on what has already been generated, not on hidden knowledge of the future. Masked attention may sound like a constraint, but it is actually a powerful training discipline. It ensures that models mirror the real conditions of generation, producing outputs sequentially in a way that aligns with human expectations of causality and coherence. The causal structure of attention is particularly important for generative modeling. In left-to-right generation, each new word must be predicted without breaking the illusion of natural flow. Causal masking enforces this by guaranteeing that no future token influences the prediction of the present one. This mirrors how humans speak or write. We do not know the future words in a sentence until we produce them. By embedding causality directly into the architecture, attention-based models avoid shortcuts that would undermine their ability to generate coherent language. This is why text produced by transformers feels natural and sequential rather than artificially spliced together. The causal design is a subtle but essential ingredient, ensuring that attention remains grounded in the realities of human communication, rather than exploiting future information that would never be available in real time. Attention dropout and regularization add another layer of robustness to these systems. Just as dropout in neural networks randomly removes certain activations to prevent overfitting, attention dropout reduces the weight placed on specific token relationships during training. This prevents the model from becoming overly dependent on a few dominant connections and encourages it to learn broader, more generalizable patterns. For example, in a sentence where one word strongly correlates with another, without dropout, the model might over-rely on that connection and ignore other relevant words. Dropout forces the system to diversify its focus, creating redundancy and resilience. It is akin to teaching a student to not rely on one source of evidence but to consider multiple perspectives. Regularization strategies like this are critical in making attention mechanisms not only powerful but also reliable in diverse and noisy real-world contexts. Despite its power, attention comes with serious computational challenges. Because each token compares itself to every other token in a sequence, the complexity grows quadratically with sequence length. For short sentences, this is not a major issue, but for long documents, transcripts, or books, the costs become enormous in terms of both memory and time. Running attention on very long sequences can quickly exceed hardware limits, creating bottlenecks in training and inference. This quadratic cost is one of the biggest obstacles to extending context windows indefinitely. Researchers and engineers are acutely aware of this limitation and have devoted enormous effort to finding ways to approximate or optimize attention so that it remains feasible at larger scales. Without such innovations, attention-heavy models would remain impractical for long-form tasks, limiting their usefulness in real-world applications that require processing vast amounts of text. Sparse attention has emerged as one promising solution to this problem. Instead of computing attention across all pairs of tokens, sparse methods restrict focus to a subset, such as nearby tokens or predefined segments of the sequence. This dramatically reduces the computational burden while still capturing the most relevant relationships. Imagine skimming a long article. You may pay close attention to sections around the main idea, while ignoring footnotes or repetitive phrases. Sparse attention formalizes this selective focus into the model itself. By pruning unnecessary comparisons, these methods extend the feasible length of sequences models can handle, pushing the boundaries of what attention-based systems can process. Sparse attention illustrates how clever engineering can make powerful ideas scalable, preserving performance while lowering cost. Low-rank approximations represent another approach to efficiency. Instead of calculating full similarity matrices between all queries and keys, approximations compress this process into smaller, more manageable computations that still capture the essential structure of relationships. It is similar to summarizing a dense report into key themes without reading every line in detail. You lose some granularity, but retain the overall picture. These approximations allow models to achieve near-identical performance at a fraction of the computational expense. While still an active area of research, low-rank methods are showing promise as a way to make attention sustainable for very large models and long contexts. They exemplify the balance between mathematical rigor and practical efficiency that defines the evolution of AI architectures. In practice, attention bottlenecks continue to pose engineering challenges. Running large transformer models at scale requires immense resources, not just for training, but also for deployment. Memory constraints, latency requirements, and hardware availability all shape how attention-heavy systems are deployed in the real world. For instance, deploying a large model in a consumer-facing product requires careful trade-offs. Attention must be fast enough to respond in real time while still maintaining quality. These bottlenecks are not theoretical annoyances but daily realities for organizations deploying advanced AI. Engineers must constantly balance ambition with pragmatism, ensuring that attention remains a strength rather than a liability in large-scale applications. One of the most remarkable outcomes of attention is its contribution to emergent abilities in large models. As models scale in size, attention enables in-context learning, the ability to infer rules or patterns from a handful of examples presented in the input. This behavior was never explicitly programmed but emerged naturally from the way attention mechanisms allow tokens to relate dynamically. It is as if the model learns to pay attention to the examples in a prompt and generalize from them to new inputs. This emergent ability has transformed how we interact with AI, making it more adaptive and versatile. It demonstrates that attention is not just a technical trick, but a mechanism that opens the door to entirely new forms of machine intelligence. Interpretability has become one of the most discussed aspects of attention. Because attention weights indicate how strongly tokens relate to one another, researchers often use them as windows into the model's reasoning process. By visualizing these weights, we can sometimes see which words a model considered most relevant to its prediction. This creates a sense of transparency, suggesting that attention provides a map of the model's internal focus. For instance, in a translation task, we might see that a model strongly aligns dog with its equivalent in another language, giving confidence in its decision-making. This visibility is rare in deep learning and makes attention particularly attractive as a tool for interpretability, offering glimpses into what otherwise remains a black box. However, attention weights are not a perfect proxy for understanding model reasoning. Just because a model assigns high attention to certain tokens does not mean those tokens were the decisive factor in its output. Other hidden mechanisms and nonlinear transformations also play a role. This means that while attention provides useful clues, it cannot be taken as a full explanation of why a model made a particular decision. Relying too heavily on attention for interpretability risks oversimplification and false confidence. Researchers caution against treating attention maps as definitive windows into how the model thinks, reminding us that interpretability in AI remains an open challenge. Attention is a step toward transparency, but not the final answer. Attention's influence has also expanded beyond transformers, showing up in domains far removed from language. In vision, attention mechanisms are used to focus on specific regions of an image, allowing models to recognize objects more effectively. In reinforcement learning, attention helps agents prioritize relevant parts of their environment. Even in scientific applications, attention is used to link relationships across structured data. This cross-domain adoption underscores the universality of the concept. Wherever information must be filtered, weighted, and contextualized, attention proves useful. It is becoming a general principle of machine learning rather than a niche trick confined to one architecture. The evolution of attention research continues at a rapid pace. Scholars are constantly proposing variations that improve efficiency, extend context windows, or refine interpretability. Some explore hybrid approaches that combine attention with convolutional or recurrent elements, aiming to capture the best of multiple traditions. Others focus on new positional encoding schemes to allow longer documents and dialogues to fit within practical limits. Each of these innovations builds on the same foundational insight that selective focus implemented through QKV relationships is the most powerful way we currently know to process sequences. The journey of attention is ongoing, with new techniques emerging that promise to make it even more capable and accessible. As a bridge to what comes next, it is important to recognize that attention, while powerful, faces limits in sequence length. Future episodes will explore long context methods, such as alternative positional schemes and novel adaptations of attention that stretch its capabilities to thousands or even millions of tokens. These advancements represent the frontier of transformer research, where the goal is to enable models to process entire books, datasets, or lifetimes of dialogue without losing coherence. Understanding the mechanics of attention prepares us to appreciate these innovations, because they extend the same principles into new territory. This continuity ensures that our grasp of attention remains central as we move deeper into the world of advanced AI systems. In conclusion, attention is the mechanism that enables transformers to focus flexibly and effectively on the most relevant parts of input sequences. Through self-attention, cross-attention, and masked attention, it shapes both understanding and generation. Regularization, sparse strategies, and approximations address its computational challenges, while interpretability and emergent behaviors highlight its surprising depth. Attention extends beyond text into vision, audio, and multimodal systems, proving its universality. At the same time, it reveals both strengths and limits, balancing immense power with real-world constraints. As we prepare to explore long context adaptations, we carry forward the understanding that attention is not just a clever mechanism, but the very heart of modern AI, enabling both the breakthroughs of today and the frontiers of tomorrow. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.